Hi, my name is Joe Tavares, and this video is the analysis of the slot edge effects on other slot conductors. Hi, this is the slot shielding analysis video. My name is Joe Tavares. Okay, so we'll begin with some basic trigonometry. The sum of the angles in a triangle always equals 180 degrees. In the case of a triangle with two equal sides, which is the R in the triangle before, I'll have two equal sides shown before. So phi, so two angles will be the same. Phi equals 180 degrees minus the position angle divided by 2. Cosine angle and sine angle. In a right angle triangle with 90 degrees, the hypotenuse is 1 unit length. This is the opposite side with respect to theta, and hypotenuse at 1. Cos theta equals adjacent side over the hypotenuse, and sine theta equals opposite side over hypotenuse. Any vector can be resolved into a horizontal component and a vertical component, and their magnitudes are shown before. So we have a vector, could be at any angle theta. The hypotenuse is 1, so the horizontal component will be sine theta. The vertical component will be cos theta. A vector is a quantity that has both a magnitude and a direction. So here I show an edge, say a slot with an edge here, and this is the edge at a certain angle called theta. In this case, I'm showing that theta equals the position angle. The position angle is from the vertical line here, which is the 0 degree point, to any position here. This edge has the same angle as the position angle. We can resolve any edge into two components, an horizontal component and a vertical component. The vertical component is cos theta, and the horizontal component is sine theta. Now this is a case where I've shown the theta is not equal to the position angle, but here theta is at 90 degrees. Again, with reference to the vertical, which is this vertical here, and it's 1 unit. So the position angle is the edge position angle with respect to the center of the core from vertical line. At vertical top, position angle equals 0. This is the vertical top. This here, the position angle is 0. So you can think of this circle as an inner core or rotor. Phi is the position angle of the edge with respect to the conductor. So phi is this angle here. So if we have an edge here, so this is the angle position with respect to the conductor. This is phi. Phi equals 180 minus position angle divided by 2. When position angle equals 0 degrees, phi equals 90. So when position is at 0, you can see as the positions gets closer and closer to 0, the blue line is almost a horizontal line. It's 90 degrees. When the position angle equals 180 degrees, which means all the way down here, the position angle is all the way down to here, the phi is 0 degrees, because phi, the blue line gets closer and closer to the radius. So phi becomes 0 as you approach, as position angle approaches 180 degrees. So that's how we look. Red is the edge angle, theta, and the direction. In this case, the first edge is outwards, so we will make the outwards then as a 1 positive unit, and all inward units will be 1 unit negative. Black is the edge position angle, so this angle here, this is the position angles. Blue is the phi angle. These are the phi angles. So right up top here is 90 degrees. As you get closer and closer to 180 degrees for the position angle, the blue line approaches 0 degrees. This is the phi angle, approaches 0 degrees. So we'll begin the slot analysis. So we're going to assume for now a straight surface, not a circular surface like a rotor. So for the tooth, we apply flux cutting, which we apply the right-hand rule, which is the same for the generator. The thumb points in the direction of the force. The index finger in the direction of the magnetic field, and the middle finger is the induced current. So for flux cutting, you apply the right-hand rule. For flux linking, you apply the left-hand grip rule. So here it is. You grab the field vector. In here, in the slot, if the motion is from left to right, here the edge, the field here is increasing. Here is decreasing, which is the same thing as increasing in the opposite direction. So for flux linking, apply the left-hand grip rule. You grab the vector with your left hand, with the thumb pointing in the direction of the field increasing. So that's how you find. So here in the slot, there's no flux cutting, but there's flux linking. Here, there's flux cutting, but the effect of flux linking, because this is increasing, this effectively they cancel. So there's has no effect on the tooth. So no B field exists in the slot since it's a shield. Flux cutting on tooth side, flux linking in the slot side, in the slot. The induced voltage is the same in magnitude and direction out of the page. So if you apply the left-hand grip rule, you'll find that the induced voltage is out of the page. If you apply the flux cutting right-hand rule, you'll find also the flux cutting, and both will be at the same magnitude. From the perspective of the conductor, so we're looking at the conductor on the tooth, the field change on the edge of the slot, the pair cancel, has no effect. From now on, this is the representation of edge field change. So when we look at the pair of edge field change, it induces 1 unit. Also represent the pair induces 1 unit in the conductor in the slot. The flux cutting also induces 1 unit in the conductor on the tooth. The conductor in the slot behaves as if the conductor was on the tooth. Therefore cannot be used for a current return path for the conductor on the tooth. I wanted to use the slot thinking that would shield as a return path for the tooth, but it can't because it induces a voltage in the same direction. Multiple slots and teeth. This was assuming again a straight surface. There's a tooth slot. The induction is 1 and 1 and 1 also. So multiple on a straight surface, multiple slots and teeth had no effect on other slots. But in reality, the core is circular. Does the position of the slot edges and the edge angles affect the conductor in the other slot? So basically, if you think about a rotor is like another slot here in this position, does this edge field changes on the slot, on the side of the slot, has an effect on the conductor in the top slot? Yes, it does, because it's no longer, this position is not the same as this position. It's a different angle with respect to this conductor. Since the circular core is symmetrical about the vertical axis, only half of the circle is analyzed for the effect of other slot edges field changes on the conductor in the top slot. Also, the analysis is normalized and done for the effect of one edge only. This edge is treated as 1 unit, 100%, and its direction establishes the positive direction. In the case below, the outward direction from the core is positive. Since the first edge, the field is outwards because it's increasing if you're moving from left to right. So this is the vertical direction, then we treat as positive, and then this direction will be treated as minus since it's inwards. This is outwards, so this will be treated as a positive. The analysis calculator is to calculate the fractional reduction from the 1 unit at the edge. So we calculate how much this is reduced. because we start with this as 1, and then we add up the effect of each edge, and it comes to, if the effect on the edge is to change from 1 to 0.6, then by symmetry the other edge of this slot will also change by 0.6, and the induced voltage will change from 1 unit to 0.6 units. So this will be the symmetry line. The analysis was done for 3 points in the top slot: start, mid, and end. The 3 results are averaged. The start is the first edge of the slot, which is the vertical. So this is the start. So this is the first edge, vertical. And the end is the other edge of the slot, which is the vertical. And this is the motion. So we'll have 3 points when we're doing analysis. We'll have a start, we'll have a middle, and we'll have an end. This is for the slot, this is for the tooth. We have a start, a middle, and end. So this is the formula, the edge effect from other slots. The slot edge angle is broken up into a vertical component and an horizontal component. The vertical component of the slot edge, so this term here, cos theta, is the vertical component of the slot edge. Sine theta here is the horizontal component of the slot edge. The sine phi here is the induction factor due to the edge vertical component position relative to the conducted position. So basically, if you look down here, looking at the vertical component, when it's right beside the conductor, the angle, or when it's horizontal direction, the phi angle is 90 degrees and the sine of phi is 1. So this is maxima at 1. If you take this vertical component as you move around down to the bottom at 100, where the position is 180 degrees, phi will be 0 degrees and sine phi will be 0. So this will be at the minimum position. Now for the horizontal component, we use cos phi, the induction factor due to the edge horizontal component position relative to the conductor position. In here, phi is at 90 degrees and cos phi is 0 degrees, because an horizontal component has no induction on a conductor because it's not vertical. But here, when phi is 0 degrees, cos phi is 1, and it will have an induction. And if it's increasing this way, the induction will be out of the page. So edge effect, so the edge effect is cos theta times sine phi plus sine theta times cos phi. Consider 2 special cases. The edge angle theta is always vertical. In other words, we're going to take the case in the left where we're going to move a vertical component all the way around to 180 degrees and see what the effect is in each position. So so theta is always at 0 degrees, and therefore the right side of the equation is always 0, since sine theta is 0, since sine of 0 degrees is 0. So we only have the left hand side for this case as part of the formula. And since theta is always 0, cos of theta is 1. So the only thing that's going to change as we move the vertical component will be the sine of phi. So in the first positions, phi is at 90 degrees, so it's vertical, so the effect is 1. On position 2, the effect will be 0.924. On position 3, the effect will be, it's at 45 degrees, phi is at 45 degrees, the effect will be 0.707. And then when you go to position 5, phi is 0, the effect is 0, which is true because a vertical component on the inductor here has no induction. So this is how it's shown between when phi is at 90 degrees and when phi is at 0 degrees. Now for the other case, the edge angle theta So we're going to do a case where theta is always horizontal or 90 degrees. Always at 90 degrees, the right side of the equation is always 0. So in this case, the right side of the equation is, sorry, should have been the left side of the equation. Now phi is equal to 180 degrees minus position angle divided by 2. So phi here is a 90, sine theta, cos theta. So we always have theta is always at 90 degrees, so sine of 90 degrees always will be 1. So the effect here is only cos phi as we move around. So in the beginning, the cos of 90 is 0. So here the effect will be 0, which makes sense because at 0 position, a horizontal component has no induction on a conductor. As we move along, on position 3, again it's 0.707. On position when phi is 0 degrees, cos of 0 is 1. That has the maximum effect, which is true because now we have a horizontal vector causes an induction on the conductor. So now we look at the effect of duty cycle. The ratio of the duty cycle is defined as the ratio of the tooth width to the slot width, also has an effect. The ratio of tooth width to slot width is about 9 to 1. Tooth is very large. In this case, the tooth is very large, the slot is very small. Here say about 1. The field edge changes as large effect on the slot and nil effect because they're so close together. These two edge effects, one is vertical, one is outwards, one will be inwards. They basically cancel. And so the induction on this will be 1 and the induction will be almost 1 unit. But in the case, the reverse, where we have a large slot and a small tooth, where the tooth to slot width ratio is about 1 to 9, tooth small, slot large, the edge field change has large effect on the tooth and nil effect on the slot. So here, the edge changes, the flux linking will have an effect, practically it cancels. So they can be treated similar to a straight line and linear case. So in a circular multiple slot and teeth, the duty cycle ratio also determines the induction ratio. It applies only for the case where theta equals position angle. This is almost like a bar magnet moving together with a conductor, where the induction is almost 0. So the induction on both is almost 0. So case of a large tooth and a small slot, induction is the same on both, 1 unit, 1 unit. Case of a large slot and a small tooth, no induction on both for the conductor on the tooth, and it is like a bar magnet moving together with the conductor. From the perspective of the conductors on the teeth, the field changes on the slot edge has no effect on the conductors on the teeth, since the pairs cancel. Each edge has an effect on the conductor on top here. Each effect is an entry into an Excel spreadsheet using the formula. The net effect is the sum of edges 1 to 8. So each edge here represents an effect on a conductor, and we enter that on an Excel spreadsheet, and then we sum them all up and we find out the percentage effect. So this is the case with a tooth in the middle. Position 1 is almost 90 degrees. This is position 1. Position 5 is around 45 degrees, which is about here, or position 4. We always resolve in each position the edge vector into two vectors, a vertical and a horizontal, and then we apply the formula for the vertical side and the horizontal side. This is the phi angle. This is the case where the tooth end is at the end. So this will be now the first position, second, third, and so on. So this is the case slot at start. This is the 0 degree position. This will be the number 1 position. And slot in the middle. So notice for the analysis, the conductor position at start, middle, or end is positioned at the 0 degree position. So we always rotate the rotor so that when we position now for the effective conductor, the conductor is always at the 0 degree position angle. And this will be the first edge effect. This is a slot the end again. We moved the rotor so that the end now is at the 0 degree position, and this is the first vector edge affecting the conductor on the end. So this is the spreadsheet that we made for each of the entries, but this case, instead of being 4, I use 10 slots and 10 teeth just to see if the number of slots and teeth has an effect. It doesn't. It doesn't matter if it's 4 slots and 4 teeth or 10 slots and 10 teeth, the effect is the same. So this is there's three tables, one for the start, one for the middle, and one for the end. And then I sum all 3 of them and I average them. So for the start, the first position here, which is 1, because this is right now on the start. The next is a negative because the edge is inwards. It'll be minus 0.98, and then the next one is outwards, but it's positive, but it's slightly less and keeps going. And so what it does, the sum comes to 0.46 for the 1. This is for the start. For the middle position, it comes to 0.5. For the end position, it comes to 0.53, but the average of all 3 is about 0.5. So now we have a different case where the theta, the angle, is no longer equal to the position angle, and we selected 2 special cases. One is for the slot here, the edges is parallel on the left side, and so we're going to build a device where we're going to put parallel slot edges on the left side. See here, they're parallel, but here is vertical, here is horizontal, and the tooth is anti-parallel. And here is the case where the slots is anti-parallel and the tooth, the edges are parallel. The following tables are the analysis for the case of 4, so it will be 2 sets, 3 analysis for start, middle, and end for the 4 slots with parallel edges and 4 anti-parallel teeth, and followed by the case of 4 slots with anti-parallel edges and 4 parallel teeth. So this is 4 slots parallel with the conductor on the start position. The sum came to 1.14, and this is for 4 slots with the conductor in the mid position. The sum came to 1.45, and 4 slots with parallel with the conductor on the end position, and the slot effects came to 1.7, but the average came to 1.433. Now it's 4 slots anti-parallels with the conductor in the start position. The sum came to minus 0.400. That means the induction analysis is in the opposite direction. This again is for analysis with the B field going outwards from inside the rotor outwards towards the outer rotor. So the average came to 0.5. So this is with the conductor in the middle position. The sum came to 0.05, with the conductor on and the end came to about minus 0.6. So the average came to 0.5. So on the other one, the average came to 1.4 plus. So I think the sum of the 2 should be 2. So I've used minus 0.5 and 1.5. So here's the summary. 4 slots parallel, the induction is 1.5. 4 teeth anti-parallel, the induction is minus 0.5, which gives 1.5. So in other words, the slot and the teeth always gives the same. This is for the parallel case, gives the magnitude 1.5 in the same direction. Here is 1 unit due to flux cutting, which is out of page because the motion is this way, and half a unit due to flux linking, red arrows, also out of the page, so the sum comes to 1.5. So for the case of 4 slots anti-parallel, on the slot it's calculated to be minus 0.5, but also on the teeth will be also minus 0.5. 1 unit due to flux cutting, out of page, 1.5 unit due to flux linking, black arrows, into the page. Note the flux linking induction is in opposite polarity to the flux cutting. So both will give, now both are into the page, but also both are at 0.5. The magnitude in direction of the slot equals the magnitude in direction of the tooth in each case. However, the parallel slot's magnitude is 1.5, while the anti-parallel slot magnitude is minus 0.5. Negative side indicates direction is reversed. This allows us to construct the device as shown on the next slide. So what we do is we put parallel edges, slots on the left side. So we're no longer going to use the teeth, because the reason for we're not going to use conductors on the teeth because we want to eliminate air gaps. So we're going to use conductors on the slots. So on the left hand side I'm going to put parallel slots, which the effect will be 1.5. On the right hand side I'm going to use anti-parallel slots, which the effect is minus 0.5, but the field, actually the field will be going downwards, will be also 0.5. So both will be in the same direction, which allows me to connect from the left side to the right side. So in review, just to review again, number one has almost as a 0.98 effect on a conductor. But number 2 is in the reverse direction as a negative effect on the conductor. Number 3 as a positive effect, but because it's more directly underneath and horizontal, it will have more effect than number 2. So the net effect of number 2 together with number 3 is a positive effect, hence why the total is over 1 unit. The net effect of number 3 is 0.83, minus 0.6 is almost plus 0.3 effect on the conductor. And the last one is vertical in the same direction as number 1, which is has almost 0.2 effect on the conductor, so making the total effect about 1.5. So again, to review, we apply the left-hand grip rule on the red vectors to determine the direction of induction on the conductor. So here's the case for vertical component where it's maximum when it's beside the conductor, but if it's directly underneath, it'll be a vertical component has no effect. On the other hand, a horizontal component was next to the conductor like this, it has no effect, but if it's directly below, it has maximum effect. The calculation was done as if the B field is outward. B field is reversed, so we'll have a positive effect into the page, negative effect is out of page. The total is minus 0.5. Basically, no difference from going from 4 slots parallel and 4 slots anti-parallel to 8 slots parallel and 8 slots anti-parallel. So I did the analysis now. Instead of using 4 slots and 4 teeth, I use 8 slots and 8 teeth, and these are the results. The sum with the conductor on the start position is 1.3. The average came to about 1.48, which is about 1.5, and the sum for the mid position came to 1.48, and the sum for the end came to 1.6. The average was about 1.5. That's why I'm using 1.5 and 5. So 8 slots anti-parallel, I did the analysis. For the start position came to 0.6. So the average came to 0.65. So maybe for the 8 is 1.4 and 0.6. But the sum of the two is always 6. It's always 2, sorry. So this is the mid position, the sum is minus 0.65, this is anti-parallel, and the sum is 0.67, almost 0.68. So conclusion, the slot edge angle affects the induction. Each angle, this is the case with each angle is the same as the position angle, the slot edge angle is the same as the position angle, and here is showing parallel edges. So the slot edge angles affects the, and two, also the slot width to the teeth width ratio affects the induction. So here a case where the slot width ratio and tooth width are the same, so it's 0.5 on the slot, 0.5 on the tooth. Here where it's parallel edges is 1.4 on the slot, and if it's an anti-parallel, which is not shown here, it would have been minus 0.6. So summary, this is summary. So on the bottom here, we're showing that the slot width is SW to tooth width ratio. The slot voltage induced is the tooth width over plus slot width times 1. So it's the factor. So if the slot width and tooth width are 5 to 1, so here it is a case where very wide slot and very small tooth, the effect is about 0.17 on both. If now as the slot's getting smaller and the tooth size increasing, now the ratio is 2 to 1, so the slot size is twice as big as the tooth size. You have 0.3 effect on both, on the slot and on the tooth. This is the induction factor. When the tooth now is reversed, now the tooth is the slot now is smaller than the tooth width, 1 to 2. You start getting approaching now 1, so you get 0.67 on both the slot and the tooth. So when here a case where the slot to tooth ratio is 1 to 5, you get 0.83 on the slot, also 0.83. This is the case where it's almost now a full unipolar configuration. But the case now on top is the 3 special case, 50% slot width and 50% tooth width. Slot to tooth ratio is 1 to 1. You get 0.5 induction on the slot and 0.5 induction on the tooth. Here on parallel edges, we get 1.5 on the slot, and also it would have been 1.5 on the tooth. And on anti-parallel, you get minus 0.5, which now is the direction reverse, is into the page. You also get minus 0.5 on the tooth. But we're not going to use the tooth. What we're going to do is we're going to have a device where we'll have the left side will have parallel slots, and the right side will have anti-parallel slot. Because the field on the right side is going to be reversed, this will also be in the same direction as on this side, so we can connect it in series. So this is how we do it. So here is the parallel edge slots on the left side. Here's the anti-parallel edge slots on the right side, the left side. So the B field goes through outwards through the anti-parallel teeth and inwards through the parallel teeth, and the induction will be always in the same direction from left to right. This is the coil that allows us to connect the coil straight through, and we'll loop on the outside through the outer core. We could have looped through the inside, but the preferred choice is to loop through the outer core outside. And this is the end of our analysis.